Unit 7 only has 2 chapters in it. It starts with chapter 26, which is going to introduce a new distribution, the chi-square distribution. There are 3 types of inference tests in this chapter, and the first one is called the goodness of fit test. This is where we want to see if an entire distribution matches that of another distribution. Assumptions and conditions, we still check randomization and 10%. We want to see, do the expected cells in our distribution all have values greater than or equal to 5? We'll be working with a table, and we want to make sure all those values have expected values that are larger or equal to 5. And lastly, all the tests in this chapter need to start as counts of categorical data. Now with these tests, there's a new distribution. So it's not a normal distribution. It's not a t-distribution. Instead, it's called a chi-square distribution. And this one looks different than the other ones. The equation that we'll use for a test statistic is chi squared. Okay, so this is a chi symbol, equals the sum of all the cells in our table, and we do this for each cell. Observed minus expected, we square it to make it positive, divide it by the expected value, add those up for all the cells, that gives us our chi-square value. The test is going to have a certain degrees of freedom, and it's marked by the number of categories minus 1. Like the t-distribution, the chi-square distribution varies based on the sample size, the degrees of freedom. Unlike the t-distribution and the normal distribution, this is not a unimodal symmetric curve. It's no longer bell-shaped. Instead, chi-square distribution is skewed to the right. It's more skewed with smaller sample sizes than larger sample sizes. So here you see degrees of freedom 1, 5, and 10, and how the peak of that distribution moves to the right as the sample size grows. The chi-square test is always one-sided. The smallest value we can get for a test statistic is 0. That's where the curve starts, and it just gets bigger from there. We only use this for hypothesis tests. We don't do confidence intervals. And since this starts at 0, okay, small chi-square values means that we have a little bit of variation or data. Large means there's lots of deviation from our null hypothesis that would give us small p-values and lead us to reject the null hypothesis. Example 1, does your zodiac sign determine how successful you will be later in life? Fortune magazine collected the zodiac signs of 256 heads of the largest companies. Is there sufficient evidence to claim that successful people are more likely to be born under some signs than others? So the way we'll identify something as a chi-square goodness of fit test is we'll be given a table like this. It's a table with just one column of values. Right, so here we have signs, and then we have the counts of those signs over here. Now, we're going to do a hypothesis test. Normally this would be phantoms, but for chi-square tests, we skip the parameter, so it's just phantoms. The reason we skip the parameter is our null hypothesis is that all these signs occur in equal proportions. And the alternative is that any one of these can be different. Maybe it's the Taurus that's different. Okay, or maybe that's actually supposed to be an equal sign, and it's the Pisces that's different. All right, there's a lot of different alternative hypotheses. We wouldn't want to write all of them. So instead, we write these out verbally. We say that births are uniformly distributed over the zodiac signs. That's the null hypothesis, is saying that all of these, the number of births is the same. Any differences that we see in this column is just the result of natural sampling variation. Alternative says that births are not uniformly distributed. So there's some months that are getting, for example, too many births, and we can't attribute that difference to chance alone. Assumptions. Let's start with counted data. So in this table, we're given the counts of how many people were born under each zodiac sign. This is categorical data counted up. Randomization. This isn't actually random. It's a convenience sample, but we're going to assume it's representative of the entire population. 256 company heads is less than 10% of all heads of companies in the United States. Expected cell. So when we talk about the expected cell condition, we're not looking at these numbers here. We're looking at how many we would expect to get in each based on the null hypothesis being true. So there's 256 people in our sample. The null hypothesis is saying that these births are uniformly distributed over the 12 signs. So if we just divide that 256 by 12, it gives us 21.33, right? That's what we would expect to get in each of these columns, in each of these cells, if the null hypothesis is true and these births are uniformly distributed. They're all at least 5, condition met. So this is called the chi-square goodness of fit test. Degrees of freedom is the number of categories minus 1, and we have 12 categories in our table. So of course we're going to let our calculator do the hard work for us, but it's important that we understand what's going on in the background. So we started with our sample. This is our observed data. It's what actually occurred in the sample. And we figured out what would we expect to get based on the null hypothesis being true, if these births were uniformly distributed. Our test statistics say find the observed minus expected, square it, divide it by the expected. So let's break it down. We start off by finding the difference. Okay, observed minus expected. We do it for each cell. We can see some of these are positive, some are negative. If we just add these together, they're largely going to cancel out and we'll get 0. So what we have to do at this point is we square all these values, which turns all of them positive. Now once we have this, we're going to divide it by the expected value. In this test, all the expected values are the same, but that's not always the case. This gives us our chi-square value for each cell. The chi-square value for the whole test is all of these values added together. So we add these all up. We get our test statistic. The sum of these is our chi-square value, 5.094. We can use this to find a p-value. Okay, we go into our calculator. We look for chi-square CDF. We go from this is always the lower off to the right, and for upper we're going to put in 999. It's just a safe value to put in because if we have a small degrees of freedom, we sometimes have to go out really far. Okay, and we get a p-value of 0.926. Now that p-value is really large. What that's telling us is that the results of the sample are not at all unusual compared to our null hypothesis. So in other words, if the null hypothesis is true, we would see results with this amount of variation or more than 9 times out of 10, 92% of the time. Okay, we fail to reject the null hypothesis since the p-value of 0.926 is large. There's insufficient evidence to suggest that births of executives are not uniformly distributed across zodiac signs. If we're asked to interpret the p-value, we do it the same way as we have been doing. Given the null hypothesis is true and zodiac signs of executives are uniformly distributed, the observed sample or more extreme would occur about 93% of the time by chance alone. Now there's 2 other chi-square tests, and the good news is that they're actually exactly the same. We do them the exact same way. The only thing that's different is the name. So the first one is called the chi-square test of homogeneity. This is where we're comparing counts for 2 or more groups, and we want to see are these groups quote unquote the same? Is the variation between the 2 groups acceptable within the range of what we'd expect by chance, or unacceptable? They're different enough where we can't attribute those differences to chance alone. Conditions, counted data, randomization 10%, expected cell, just like goodness of fit test. Degrees of freedom changes because we're not going to have a table with just one column anymore. This time we're going to have both rows and columns. So degrees of freedom is number of rows minus 1 times the number of columns minus 1. Example 2, we want to know whether the choices made by high school graduates and what they do after high school have changed across 3 graduating classes. So we have graduating classes from 1980, 1990, and 2000, and we're comparing what they choose to do after high school and saying, are these differences attributable just to natural sampling variation, just chance alone, or are their decisions different across the 3 decades? Hypotheses, the post-high school choices made by the classes of 1980, 1990, and 2000 have the same distribution. They're homogeneous is another way we can write this. The prefix homo means the same. Alternative is that they do not have the same distribution. Assumptions and conditions. The data are counts of the number of students in the categories. Randomization 10%. This actually we don't need to check because we're not generalizing. We're not talking about all the students across all the high schools in 1980, 1990, 2000. We're just saying, is our sample from 1980 the same as, quote unquote, 1990 and 2000? Since we're not generalizing, we're not using inference and applying our conclusion to a larger population. So there's really nothing that we need to check here. Now the other test, we do check these. So I'm just going to say we'll go ahead and check them in all cases because you're used to doing it, and we'll just make it automatic. Expected cells are all at least 5. The way we get these, we're going to talk about in class, but it's just the total row number, if we add these all up from the slide on the original page, times the column number divided by the total. Name the test. This is a chi-square test of homogeneity with 6 degrees of freedom. That comes from the number of rows. There's 4 rows, 2, 3, 4, 3 columns. So 4 minus 1 times 3 minus 1, 6 degrees of freedom. Our test statistic is always the same regardless of which type of test we're doing. So observed minus expected, square it, divided by expected. So here we have 1980 college. 320 is the observed, subtract the expected, square it, divide it by the expected. All right, employment, 98 minus 59.52, square it, divide it by 59.52. Okay, we're going to let the calculator do this. It's going to add them all up for us. We get a chi-square test statistic of 72.77 and a p-value of 0.0001. That's a small p-value. We'll reject the null hypothesis. There's sufficient evidence to suggest that the choices made by high school graduates have changed over the 2 decades examined. The third type of chi-square test is called the test of independence, and it's exactly the same as the one we just did, the test of homogeneity, with the exception that they're comparing 2 different things, and that's why they're named differently. We're no longer just comparing samples, so we do have to check that randomization and 10% condition. So like I said, we'll just go ahead and check it all the time because it's automatic and we do it for every other test. So in a test of independence, we have 2 variables on a single sample, and we want to see, are these 2 variables independent of one another? Now, I'm not going to work through the whole problem because it's exactly the same process as the one we just did. I'm just going to show you an example of it. A public opinion poll surveyed a simple random sample of 1,000 voters. Respondents were classified by gender and by voting preference. Results are shown in the table below. Is gender independent of political party? Right? So when you see a sentence like this, straight up asking, are they independent? Obviously, it's a test of independence. Other key clues here is that this time we just have one sample. They talked to a sample of 1,000 voters, and they're classifying this sample on 2 categorical variables, their gender and their voting preference. We're testing to see, are these independent? Okay, if they are, it won't matter if you're male or female. You're just as likely to be Republican, Democrat, or independent. If they're not independent, maybe being male, for example, makes you more likely to be Republican. When choosing which test to use, there's a few things that'll give you hints. So for a goodness of fit test, we look for a table that just has 1 row or column. That's a pretty big giveaway. If it says something like, does the data match the expected distribution? Goodness of fit is testing to see if they match. Or is the data consistent with the proportions given? That's another thing. We're seeing if it matches the expected proportions. When a table has multiple dimensions, like 2 by 2 or larger, we're going to either do a test of independence or homogeneity. We can't do goodness of fit once we have a table that has both rows and columns. We're going to do a test of homogeneity if it says something like, are the sets of data the same versus different? Remember, that prefix means the same. Are the 2 groups homogeneous? Okay, link these words together. So if you see 1, we know it's a test of homogeneity. We'll do a test of independence if it asks, is there an association between these 2 variables? Or if it straight up asks, are the 2 variables independent?